Hi, welcome back. In this lecture, I want to talk about how to add type annotation to Cython code. It turns out that adding type annotation to our code, our Cython code, is probably the best optimization that we can do to increase the performance of our code. By the end of this lecture, we will be able to annotate with C-like static types the Cython codes using cdef. We'll also be able to understand and state the performance advantage of using type annotation when using Cython. The annotated Cython code show that all our numeric work is also calling back into the Python as we are using the higher level Python object. So here is our annotated code, and you see here that we have all the yellow lines. That is, we are talking a lot to the Python virtual machine. How we optimize? Well, as I said in the previous lecture, probably the best way to improve the performance is to convert this higher level Python object into local C object. And then after we have been doing the numerical coding, we need to convert result back to the higher level Python objects. An important note that I want to make in this lecture is that when we add Cython types, we are adding non-Python code for the first time to our PyX file. So far, our PyX file was just a Python file, and then Cython was doing all the work. However, in this lecture, we are going to annotate with Cython types, and we are going to lose the pure Python components. That also means that we're going to lose all the interactive nature of developing in Python in the interpreter. How we add the type annotation to our Cython code? We're going to use the cdef declaration that will allow us to declare variables inside the function body that is written in Cython. The cdef keywords let us to declare variables inside the function bodies. So this declaration must be at the top of the function. To follow up the C specification that requires to have the variable definition at the beginning of the code or the function. So you see here an example of using a cdef definition here. So we have our previous PyX code that was a pure Python code that we have it here. What we're adding here at the beginning of the function, follow the C convention of putting the definition at the beginning of the function, is this type annotation. So we use the cdef, and then we tell the types of the variables we want to use. We can use int for a signed integer, unsigned int for an integer that can be only positive, and then double complex for double precision complex number. So we use cdef, and then the type, and then the name of the variable. So these I and n are basically counters, so we can define as unsigned. And then we have the two numbers that are complex number. We want to have them in double precision, so we have double complex z and c. So we are going to have this Cython type annotation. As you see here, it's very simple. We just add the definition at the beginning of our function. The important point here is that at this point, our Cython code is not a pure Python code, but we add this Cython part, so it's not anymore a Python code. So we lose some of the advantages of being a pure Python code. You might also wonder if you could add a type annotation to the list that we pass in or we are working on. Well, it turns out that yes, we can actually use the list keyword, but it has no practical effect for this code. The list objects still have to be interrogated at a Python level to pull out all the contents, and this is it's very slow. So we won't have any benefit in using the list. If you run Cython -a and then the name of our function, so is Cython fn.pyx, we will have a new HTML file that we can open on a web browser. If you're looking at, if you look at the output, we saw that the fact of adding types at the beginning of our function is reflected in the annotated output. In particular, we have more white line. Actually, we start having the white lines. People were all yellow, more yellow, less yellow, but we have all yellows. What we see that the lines 12 and 13 that are at this, and these are the most frequently called lines, have now turned from yellow to white, indicating that they no longer call back into the Python virtual machine. Because of this, we can anticipate a speed up when compared to the previous version that was not using type definition annotation. Now we want to see what is the speed up. We call Python Julia Py that is calling our Cython fn.pyx with the type annotation. You can see here on the slides that the entire code is running now on 0.35 seconds. In the previous version, with the Cython but without cdef, this took 2.1. If you see the overall impact on the performance of using Cython and the type definition, we see that we are running 8 to 10 times the speed of the original Python version. It's important to note that the reason for we are gaining speed is that more of the frequently performed operations are actually now pushed down to the C level, so to very low level, and compiled to machine language. Another possible optimization that we can do is the so-called bounce checking and remove them. The goal of the bounce checking is to ensure that the program does not access data outside the allocated array. So if you have an array, there might be a loop that tries to go out of the array. So we want to have checking to tell us, oh, we are trying to access outside the array area. In C, it's easy to accidentally access memory outside the bounds array, and this will give unexpected results. By default, Cython protects the developer from addressing outside the list limits. So this protection costs a little bit of CPU time. So you need to check that we are not going outside the array. So they cost some time. So a possible potential optimization technique is to disable bounce checking. This is typically safe unless we are performing some calculation for array addressing, in which case we have to be very, very careful that we are stay within the bounds of the list. How we do that? Well, this is very simple. What we can do, we can add at the beginning of our call the so-called pragma to talk directly to Cython. To add the pragma, we use pounds Cython and then semicolon, and that will tell you that we want to talk to the Cython and to the compiler, and then we set it up bounds check equal to false. So this will provide information to the compiler to remove the bounds check. There are other different ways. For instance, we can add the decorators, but one simple way is just to add at the beginning of our Cython function these lines of code. If we remove that, then we see that we get slightly some benefits. We are running now 0.330, but the time that we save is very little bit time. And there is also because this occurs in the outer loop, it's not in the inner loop, which is more expensive. So it's possible to disable bounce checking, but in this particular case, it doesn't give little to no benefit. This is the last slide of my lecture. To summarize all the points, Cython allows us to define types using cdef. Type definition occurs at the beginning of the function here. There's a mistake, so this is at the beginning. This is the important point to follow the C convention. The third point I want to make is that static cdef types provide a great speed up in computation. In this particular case of Julia set code, it gave up a speed up of 10 times speeds. So it's very important optimization. Define types in our Cython code. This is the last slides, and talk to you soon.